So who has a question about any part of the course, about the example sheets or whatever?
In the definition of epsilon regular,
Yeah.
I can say something is little n squared.
Right.
Little o n squared regular. Like the not fixed epsilon.
Ah. So can you take something to be little o1 regular?
Yeah.
So there's two different ways of answering this question. So I wouldn't. So it's best not to. Though in some sense that is what we're doing. So because in all of the proofs, epsilon is not quite always, but essentially always the smallest parameter, then we are really we're taking epsilon to 0 slowly. I mean, often with these, when you have various constants, which are small, you're taking them all to 0 as n tends to infinity, but at different speeds. So they're all little o1, but if you use little o1 for two of them, then you have to worry about which one's bigger. So because we care about the relative sizes of these things, it's best not to write that. So I would encourage you to always write epsilon regular, but perhaps think of it as being little o1. But I mean, so in some sense, like in these proofs, maybe you have, so it's in the triangle removal lemma. What do we have? There's a beta, which is much smaller than epsilon, which is much smaller than delta, which is much smaller than alpha, which is much smaller than 1. Right? They're all little o1, actually.
Yeah.
But you really care that they're about the relative sizes. So.
But I can say this speed.
Uh,
It has this speed.
yeah, right. You can if you. I mean. Yeah. So I mean, I guess strictly speaking, this notation means these things are all little o1. They're all members of the family little o1. Right? They're all equal little o1 means they're in some family of things little o1. But right, when one uses little o or big O notation, it's normally because we don't care about big O, the size of the constant. Here we don't care about the rate at which they go to 0. So we think of them going to 0 arbitrarily slowly.
So right. If I respect the relation of them, I can say the order of the epsilon.
I mean, can you determine it, do you mean? Or yeah. So right. So one can read out of all of these proofs a rate at which epsilon goes to 0. But it'll be something like log star of n. It'll be very slow. Or 1 over log star of n. Because when you apply regularity, n should be bigger than 2 to the 2 to the 2 to the 2 to the 2, a tower of 2s of height 1 over epsilon to the 5. So epsilon is automatically at least the inverse of that function. Yeah. So it goes to 0, but very slowly. Yeah. Okay.
I have a question.
Yeah.
I want you to repeat the proof of the chromatic number, of the lower bound on the chromatic number of Gn 1/2.
Okay. Okay. Very good. So. Right. Chromatic number of Gn½ is 1/1 times n over 2 log to the base 2 of n. Right? Okay. Right, so
first, you mean with high probability?
With high probability, thank you. Yeah, sorry, thank you. Right. So first observation, chromatic number is at least n over alpha of g for all g, deterministically, and this implies that chromatic number of GMP, G½ sorry, is at least 1 and over 2 log to the base 2 of n with high probability. That's not the bound you wanted. What do the other bound?
I mean,
You want the upper bound.
The lower bound.
Sorry?
I didn't understand the
The lower bound, sorry, the lower bound, yeah. Okay. Okay, so is anyone happy with this? So this is because the independence number of g½ is with high probability at most 2 log to the base 2 of n. That's just exactly the proof of the lower bound of Ramsey.
Sorry, this is the part I don't understand. The other part I understand.
Ah, okay, this part. Ah, sorry. So it's the bound is in upper bound of the independence number. That's what you're saying. So lemma alpha of g½ is at most 2 plus low 1. I think we need even better than this. 2 log to the base 2 of n with high probability. This? Ah, okay. So this is exactly the proof of the lower bound of the Ramsey number. So what do we do? What are we trying to show? We're trying to show that with high probability, g½ does not have an independent set of size 2 log to the base 2 of n. Right. So let's let xk be what? The number of... Yeah. Independent cake sets in g½ where k is going to end up being this guy. Right? And notice that k, if k is 2 log to the base 2 of n, what is n? Yeah, root 2 to the k. Right? Which is our bound on the Ramsey number. Not coincidence. So, what's the expectation of xk? It's in a half, so yeah. So 2 to the minus. Yeah. Which is at most. En over k, in this guy. 2 to the minus k minus 1 over 2 to the power k. Now, n equals root 2 to the k. Right. So this is e over k, and then there's a root 2. Which tend to 0 as k tends to infinity. And the final step. Why is this a good thing to bound? What's this at least? Xk is at least 1. So the probability xk is at least 1 tends to 0. So with high probability xk is 0, which is the statement. Okay. Questions? It's okay? Does anyone want me to prove the upper bound? Or remind you how it went? No? Yes? Okay. So, what was the upper bound? So the strategy was as follows. We're just going to pick the color classes one by one greedily of the right size. So what we're going to try to do is, so here's our world, our G. We're going to pick an independent set of size roughly 2 log n. Okay? If we can find one. We make that color class 1. Then we look at the rest of the world. And say, okay, if we can find independent set of the right size, pick it. Color class 2. And so on. Color class L. I'm going to wait until we run out of large independent sets. And the claim is that here, when we run out, we'll have very few vertices, like many fewer than n over log n. Right, so the claim is, I mean, this is not a proof. We're going to state a lemma. But we can choose independent sets, disjoint independent sets, of size roughly 2 log to the base 2 of n. And we can do it until we have fairly few vertices left. And then what's our colouring? We colour class 1, 2, 3, 4 up to L. And then each vertex here gets another colour. Then the chromatic number, so if this is M, so M vertices here, and L colour classes, then the chromatic number of G_1/2 is at most L plus M. Right? Just obviously. Okay, so we need to show, so how large is L? L is at most n over roughly 2 log to the base 2 of n. And m is small, plus n over log n squared. Right? So that's what we want. Okay. So if we can prove this, then we're happy. So what does the lemma say? The lemma says that the probability that the independence number of Gn_1/2, perhaps I'll say Gm_1/2, is less than 2 minus epsilon times log to the base 2 of n, is less than or equal to what? So I want this to be true for all m at least n over log n squared. I want this probability to be small enough that I can take a union bound over all subsets. So I want this to be much smaller than 2 to the minus n. So, before proving the lemma, why does the lemma mean this argument works? Yeah, so I want it in a slightly different order. So that's essentially right, but we'll just be a tiny bit careful. So the way to make clear one isn't cheating is say, right, at the beginning we're going to ask if Gn_1/2 has a certain property. The property that we want, so this implies that with high probability, every subset of the vertex set of Gn_1/2 of size at least n over log n squared has this property. The independence number of Gn_1/2 restricted to S is at least 2 minus epsilon log to the base 2 of n. And what's the proof of this? How do you deduce this from the lemma? Yeah, so I can put equals here, right? Yeah, it doesn't change anything to put equals. Right? Independence number is at least this big for these guys, it's bigger for the other ones. And
you have 2 to the n.
right, there's at most 2 to the n subsets of 1 up to n. So, yeah, it's union bound. It's just the union bound. Just sum over all sets, the probability of failure and it's little o1. Right? Just Markov or the union bound. Okay. Right, that implies this. But now this is the condition we want. So this is, yes, please.
Can you repeat the last one?
So the proof. So the probability. So the probability that there exists an S that fails this right, is at most the sum over all S of the probability that it fails, which is at most 2 to the n times the probability it fails, we just proved as this. So less than this times 2 to the minus n. Does it make sense? I'm just saying, just add up for all sets the probability of failure. That gives an upper bound on the probability of failure, and it's small. Yeah. So this is an important idea, right? That what we can do. Oh, sorry, that I've just erased. I mean, it was just an. Right, that we can just add sum over all set to the probability of failure and the probability small. So the important idea is that we can use this large deviation inequality. The probability this is very, very small for a particular set to show probability doesn't happen anywhere. What we've proved is a kind of quasi-randomness property for g1/2. I mean, g1/2 is random. We're not using that. We're using this property. And this you can think of as being a quasi-randomness type property, that every large subset has an independent set of the right size. Right? That's a deterministic property which this graph shares with a random graph. Any graph with this property, you might say, sort of informally, that it's quasi-random. So when we say a quasi-randomness condition, epsilon regularity is not the only quasi-randomness condition by any means. But there are lots of ways you can say that a graph is quasi-random, is random-like. Here's just an example. Right? So often, a good way of proving things in random graphs is to first show your random graph with high probability has certain nice properties, and then showing deterministically any graph with that property has the property you want. Right? With those family properties. That's what the proof is doing here. Right, so once you have this, then this works, right? Because you just greedily, okay, your initial set is S, it's bigger than this, so it has a large independent set. And then repeat and repeat and repeat and repeat. When you fail by this property, you must have at most this many vertices, and now you're done. Right? Okay? So how do we prove this? Yeah. So we prove the lemma. Huh? Yeah, Janssen, not Jensen. Jensen is convexity, Janssen is. Yeah. So proof Janssen. So what do we do? Perhaps I did this a little bit quickly in class. So yeah. So what's our universe? So so should we restate the Janssen inequalities? That's a good idea. Theorem. subset of n a p random subset. What do I mean? I mean the probability that I is in S equals P for all I, all independently. Okay. And let's define BI to be the event that AI is contained in S. Then, and let mu be the expected number of these things. So sum of probability of BI over I, and delta be the sum over I tilde j probability BI intersect BJ. This means that AI intersect AJ is non-empty. Then probability, the intersection of the BIs of I equals 1 to m. BI complement, none of the bad events happen, is at most e to the minus mu plus delta over 2, e to the minus mu squared over 2 delta if mu is big least delta. I'll put something around this to make it. Okay. Sorry, thank you. Very good. Thank you. Okay, so how are we going to apply Janssen? What is n? What are the sets A1 to m? Right, so n equals n choose 2. AI, so A1 up to AM are the not independent sets. Yeah, so let's put this equal to K. Call the K sets. So M is n choose K. And P is okay. So what are mu? Right. So the bad events are that a particular set of edges. Yeah, sorry. So I should say they are the not quite. So they are the edge sets of the cliques of size k, right? Okay, so for each kk in kn, ai is the set of edges of. Right? There's an ai which is the set of edges of that clique. Yes. So so what's happening? The event BI is the event that all of those edges are present, which is not what we want, right? We want independent set, not clique. We just turn it upside down, right? Really, the AIs are so the S is not. S is not g and a half. S is the complement of g and a half, which is also g and a half, right? I mean, a non-independent copy of g and a half. Right. Okay. So what is mu? Yeah.
It's about M and N, because it's M.
Oh, sorry, and this is different M. Yeah, what should I call this one then? Or should I have a different? Maybe this one doesn't matter, right? Sorry. Let me get rid of this one. L. Yeah, thank you. Okay, what's mu?
N choose K.
Uh-huh.
1 of
Yeah. I mean, the thing we just had, right? That is, so we want mu to be big, right? So we want a lower bound on this now.
N over 3 over K.
Yeah, exactly. 2 to the minus k minus 1 over 2 to the k. And now k is this guy. So n, what's the right way to do this? So maybe I'm going to, just to make the calculation slightly easier, change the definition of epsilon. 1 minus epsilon times 2 log the best 2 of n. Just so that then I can say that, what can I say? Sorry, 2 to the minus k over 2 now is, for this bit, is 2 to the minus 1 minus epsilon log n, which is n to the minus 1 plus epsilon. Right? Is this okay? So I can get rid of this 2 to the minus k over 2, put n to the minus 1 plus epsilon. This just becomes n to the epsilon. Right? Yeah. Yeah, exactly. N to the epsilon. So this equals n to the epsilon over k root 2 to the k, which is huge because k is like log n. Right? So this is at least n to the epsilon k over 2. Right? Easily. Okay, so mu is at least n to the epsilon k over 2. Let me get rid of the calculation. Just take save some space. Okay, what about delta? Delta should be at most something. So now it's a little bit tricky because we have to consider pairs of cliques intersect in some amount. Right? So it's not hard to write this down, and then you have to bound all the terms. But perhaps just to save time now, I know I did this last time, but really, I mean, really it's just something to do at home. The two worst cases are sort of clearly, okay, so what happens? The cliques could be disjoint, but then they don't count. They share vertex, they also don't count. They've got to share at least an edge. Right? Sharing an edge is very expensive because it's not very likely, right? You have two sets of size log n. Pick two random sets of size log n. How likely are they to intersect? Very unlikely. Right? The probability they intersect is basically, well, there's log n squared choices for the pair vertices that are the same. You lose a factor of n. It's like log n squared over n. Yeah? We're summing over all of them. So you can think of them as being random for the purposes of saying how likely things, like what the contribution to the sum is. Yeah, so this random thinking is quite useful for estimating when we're summing over everything. Yeah, thank you, good question, good point. Right, so two k sets, the probability they intersect in a vertex is something like k squared over n. Right? Choose a vertex on the left, choose a vertex on the right, they're going to be the same. That costs you a factor of n. That's happened twice, so it's squared. And what you gain, there's one edge that you don't have to count twice. So you gain a factor of 2. Brilliant. I mean, nothing, right? You gain nothing. Right, so you've basically, this is like 1 over n squared. Right, so you would expect your delta to be something like mu squared over n squared. And that's actually what it is. OK, what's the other bad case? The other bad case is when they're almost the same. So you can take them to be exactly the same. Then you just get mu, and that's not counted here, right? So they have to be different as well. So they're different, but as similar as they could be is when they look like this. Right, and then it's a bit more complicated. Then this is a bad way to estimate. The first one, how many did you get? You get basically mu of them, right? The expected number. And then how many do you get for the second one given the first one? Well, you get to pick this vertex times n. And all of these things have to be non-edges. So it's 2 to the minus k minus 1. So this is sort of mu squared times this, which is like mu squared over n squared. And the other extreme case is mu times n times 2 to the minus k. And everything in between is worse. So, I mean, you have to write it down to check, but you should convince yourselves that either if the intersection is small, it's like this but worse. If the intersection is large, it's like this but worse. Right? And so what's the point? 2 to the minus k is what? It's like 1 over n squared. 1 over n to the 2 minus epsilon. So this is like mu over n. So delta is basically either mu over n, so the max of mu over n and mu squared over n squared. So it's a calculation. I'm not going to make you do it in an exam, but all of you should be able to do it at home. Right? I mean, I'm not saying it should take you 3 minutes, but you sit down and think about it. This is not quite true, right? So at most, let's say n to the 3 epsilon times this or something, right? Does it make sense? Right, so either it's much smaller than mu, in which case you get this, or it's much smaller, it's mu squared over n squared. I mean, actually, we know this is big, right? Mu is at least n to the log n. So mu is huge, so this is the bigger one, right? Mu squared over n squared is the bigger one. Right? You're all looking extremely unhappy. I don't understand why. Tell me why you're extremely unhappy. I mean, I'm not claiming to give you all the details of the proof. If you want me to, then I can, but you're going to like it even less, I think. So who votes that I give all the details of this proof? Who votes we talk about something else? Okay, something else. Right. Okay. Okay, but then you're done, right? Then you just plug in Janssen and you're done. So really you get something like 2 to the minus n squared over some log n to the, I don't know, 5 or something. Right? So you're something much, much stronger than we needed. You don't just get 2 to the minus n, you get 2 to the minus n squared almost, because your delta is like mu squared over n squared. Right? So ignoring all this justification, I claim delta is smaller than something like mu squared over, sorry, because I got an epsilon. Yeah, so maybe I don't quite claim that. N to the 2 minus, I don't know, 3 epsilon or something. N to the 2 minus 3 epsilon. Okay, and then we just apply this guy. Yeah.
Is there any intuition that tells us we should use Janssen in this problem? Like,
Should you what, sir? Use Janssen?
yes.
Yeah. So, well, I mean, you need to prove the lemma. Yeah, so if you want to prove a lemma that says, I've got a bunch of events, what's the probability, and they you know, mostly independent, but there's a bit of dependence that I don't like and I can't control, and I want to prove a very strong bound on the probability that none of them happen, Janssen is your go-to inequality. This is like the inequality for doing this kind of situation. So you've got a bunch of events. I mean, you need to be in like GMP or something, right? You need to be in this world. Right? You've got a bunch of events of this form. They're all primitive events. Events of the form, does a certain thing exist? But they overlap in complicated ways. It may look, I'm not sure how specific this looks to you. It's somewhat specific, but it comes up in a lot of situations. It's a very useful inequality. Right? There are a lot of times when you're in this situation, when dealing with random graphs or random objects, or counting objects as well. I mean, not just even if you're counting things, where this is the thing to do.
I have a question. You use the second bound, right? How do you, in this setup, how do you prove that delta is?
Right, so I should have proved also this is really sort of roughly correct. So why is delta this big? Because these things, this really is the order of magnitude of this thing. Right. Yeah, so I'm talking nonsense. It's actually better than this. It really is something like 2 k squared or whatever. I mean, maybe 2 is a bit. It is roughly k squared over n squared times mu squared. That's really the probability of this thing. Or really the contribution to delta of these things. And mu is huge, so this is much bigger than, this thing is much bigger than mu. Yeah, so the delta is dominated completely by things of this form. Okay. Next question? Oh, are there more questions about this? Or we should move on, probably. No other questions? Okay, so I'll tell you about something else. Sorry? Yeah, anything from the course, anything from the example sheet, anything you like. I mean, anything outside the course that you... I mean, all mathematical questions answered. Yeah?
When will you send the list?
Well, whenever. It's not really for... Sorry? I mean, the lister is not, it's not really part of the assessment of the course. The lister is for you to do to help you with the exams. So you can send it. I mean, so you should send it.
No, I mean...
But it doesn't have to be before the exam.
You send the third list.
Oh, sorry, what is the third lister? Yeah, sorry, I forgot. I was going to say it, but now it's kind of late, right? So maybe now I won't. Yeah. Or maybe I'll send it to you just to do for fun afterwards or whatever.
And did you say, have you just said that the second lista we can send it to you after the exam?
Yeah, so maybe by the end of the month or something. Yeah.
The end of the month is...
Or by the end of Carnival or something. So yeah, Volner said he's going to correct it the week after Carnival or whatever. So yeah.
Sorry, you
Yeah.
are not sending the third list?
I mean, I might send you one, but it's for fun. It's not for, yeah. Okay.
This one course is for fun.
Yeah. No, that's the point, right? I mean, it's not, you spend all year at universities doing courses that you have to do for, right? This is to see some fun stuff. So there are no more questions. So we're going to do some, oh, go ahead.
We
Uh-huh.
showed this, and that the problem asked to show, of course, that's not the problem, but second part
Aha.
of the problem.
Right, so it's 2-point concentration. Fun, okay. Uh-huh.
I think I have a strong belief that it is false.
Aha, okay. What's the argument? So sorry, the question, I should write the question. So it's related to a stronger version of one of the lemmas we proved here. So claim is that for all n, there exists k such that, with high probability, the independence number, or the clique number, or whatever, of g and a half. Did I do it for g and a half or for?
GMPN.
Sorry, GMPN.
Yeah.
So for all GMP. Okay. P. Sorry, P depends on. Yes. Okay. So for all n and p, there exists k of p and n. Whatever. I mean, okay. So p is a function of n. So such that with high probability, the independence number, the clique number,
Yes.
the maximum L such that, or R, per se, such that KR is contained in GNP is in k plus 1. Now you're going to tell me it's false if P is sufficiently small or something. No, I don't think so.
Yeah,
Seems
I
okay.
thought we could pick P.
I think it's fine.
P is such that.
Maybe it's very close to 1. Sorry?
Yes.
Ah, so if you pick P to be so it's almost 1, then you don't know whether you've missed 1 edge or 2 edges or 3 edges or something like that. Is that what you want to tell me? So maybe I should take P to be at most a half or something stupid. 0, a half. Did I get rid of your count example?
No, the start changes. I'm sorry, this is false.
So it might be false. Let's just think about it. If P is very close to 1. So suddenly really it's flipped around. So you're looking for this very large clique. So the question is, so suppose P is 1 minus 1 over n squared. The number of edges you miss is Poisson. So it's not concentrated. So it could be 0, 1, 2, 3, 4, 5, or whatever. It could be up to as big as log n. And if you miss 0, then you get a clique on everything. If you miss 1 edge, you get a clique on everything but 1 thing. If you miss 2 edges, then you get a clique on everything but 2 edges. Yeah. Yeah, so it won't be true when P is very large. It's probably true. Yeah, so up to pretty close to 1. So maybe I put 1 minus epsilon or something.
Why won't it be true for P very large? Because you can put k equals n, right?
You can, but so let's say it again. If P is 1 minus 1 over n squared, so not arbitrarily large, with that value, then the number of edges that you miss is not concentrated. So you can't expect to have this kind of concentration. Yeah, so there should have been a condition that said that P was at most 1 minus epsilon or something. Or maybe it's even like 1 minus 1 over n or something. I mean, really, probably you can go pretty far.
Okay.
But the point of it is supposed to be do it for P small. Yeah, so for P less than a half.
But even for P very small, it still holds.
Yes, so if P is 1 over n squared, then you have a bunch of edges, but you won't have a triangle. You're very unlikely to have a triangle. So your clique is either 0 or 1. So 1 or 2. Yeah. Yeah. Do you want to prove it?
I think.
Okay. Yeah, this is a nice fact. Right, quite surprising concentration, right?
Is there a generalization of triangle removal then? Like clique removal then?
Yes. And proved in exactly the same way. Yeah, so exactly the same proof works. Right, so if you want a copy of the clique, so what's the proof? So do you want the clique or you want a general H?
If the statement is short, I want the general H. I mean,
Yeah, yeah. I mean, the statement's the same, right? So for all H and alpha, there exists a beta such that, do I want an n0 as well? Or I want n0, right? An n0 such that if G is a graph with at most beta n to the v of h copies of h, then there's a set of edges of size at most alpha n squared such that G minus S is chromatic number of H minus 1 partite. Know what I mean? No, I'm talking nonsense. What am I talking about? So there's no copies of H. So I started writing a different statement. Yeah. So so you destroy all copies of H.
I'm quite surprised that you still have n squared.
So what would you? I mean, but how else could you? What else could it be?
Yeah.
Right. There's only n squared edges. Yeah. So what's the proof? So you tell me the proof. Yeah. Right. Szemeredi. Epsilon is going to be small. K0 is 1 over epsilon. So we have this partition. Vk. We have the reduced graph. Maybe I don't even need to write the definition of the reduced graph anymore. So what are the two cases?
If there is a click, you can use embedding lemma again.
Right. So if we let the Kr in R, where R is the chromatic number of H, this implies
You have delta density to reduce graph, right? You introduce a new variable, or you have alpha density?
no, it's delta density, right? Sine regular delta dense.
You want to choose delta later, right?
So delta should depend on alpha and H, and epsilon will depend on delta as well. So yeah, so there's something to do here. So let's think about it. There's an extra interesting step here, I think.
Here in the case one?
No, so so let's finish case one. So case one says, by the embedding lemma, that you have many, so you have at least how many copies? It was like delta to the e of h times n over k to the v of h copies of h, right? I'm just set this to be b. So beta to b, delta to the e of h, 1 over k1 to the v of h. Okay, so case 2, so there's no copy of kr in R. So what we said before was, now life's easy. Just remove all of the few edges and side parts, between sparse pairs, between non-regular pairs. That's few edges. That's fine, we can throw them away. And now we've destroyed all the triangles. So now we've destroyed all the copies of kr. But why have we destroyed all of the copies of h?
So what did we delete here?
So we should. So we should remove the edges inside the parts. Between non-regular pairs, and between non-dense pairs. Right. So there's a most epsilon n squared here, a most epsilon n squared here, and the most delta n squared here. Right. So we've removed fewer than alpha n squared. But have we destroyed all the copies of h? If h were equal to kr, then yes. But if not, I mean, what if h is C4? So h is bipartite. So R is 2. So there's no edges in R in this case. So we've removed everything not in R. So we're happy. Okay, so if H is bipartite, then we're happy because there aren't any edges in R by this case 1, and so we've removed all the edges here. They're just saying it's sparse. Just saying if you don't have a sparse graph, you have many copies of any bipartite graph, right? Which we already knew basically, but okay, here's another proof of it. Okay, so what if H is K222, which is this graph? Okay. Right, so that's correct number 3. So there's no triangle in R, but R might have lots of edges.
I have a
Yeah.
idea.
Mhm.
Maybe if we change case 1 to say if H is contained in R, we can still use embedding lemma in a way. And in case 2, we use Erdös-Stone to bound the number of edges in R.
Okay, so yeah, we can do that. So R doesn't have too many edges. So in this case, R wouldn't have more than k squared over 4 edges, say. But that's still quite a lot of edges. Right.
Maybe use Erdös-Stone, so there are few edges to remove to make R minus 1.
So again, that would these extremal things, they tell you that so any small limit stability tells you if you're close to the extremal number of edges, you're applying to R perhaps, then you can say something. But what if you have fewer than that? Right? It's still lots of edges. So let's just think about this case here. Yeah.
It has triangles, right?
It contains triangles.
And are done.
Right.
So, like, if you remove all the other parts, R is at most like
Yeah. Okay. So sorry. So this is you're quite right. This is a bad example. So let's go with a better example. Here's one. C5. So we've destroyed all the triangles. But we might have a C5. We might have some other object that contains it. So what do you suggest we do? I mean, if we remove, say we remove all the copies of H, so suppose we, instead of removing the triangles, we remove the C5s. Well, then you're still in trouble, because you can find this guy inside here, right? Let me try. 1, 2, 3, 4, 5. Right. Okay. So we need one more idea.
Why can you do this?
So I'm saying that if this triple were a triangle in R, then you would find lots of C5s in it by the embedding lemma. So yeah, why can you do it? Why can I draw C5 in a triangle like this? Yeah, because the chromatic number of C5 is 3. Right. Right. I mean, that's exactly why. So, what's the extra idea? We need one more little idea. I think just one more little idea. So what would you do for C5? Just for C5. I think if you can solve C5, then you'll see the pattern. So prove the C5 removal lemma. So I'm saying so we can't remove the triangle because that leaves the C5s. We can't remove the C5s because that leaves the triangle. So what can we do? Remove both, right? Remove both. Right? If there is a triangle here, then you have lots of C5s. If there's a C5, you have lots of C5s, so you don't have either. Is there anything else we could find a C5 in? I mean, maybe, maybe not. Let's just remove all of them, right? Just remove all of them. There's only a bounded number of them, right? There's only a bounded number of ways of putting a bounded graph into... I mean, it's a bounded number of colorings of the vertex set, basically, right? Yeah, with at least 3 colors. Just remove all of them. If any of them are there, then you have millions of copies of H by the embedding lemma. If none of them are there, then you don't have any copies of H. Right? Because how are you going to find a copy of H if you've removed all of these guys? Every edge of H has to correspond to a copy of an edge in R. So your copy of H gives you a coloring of the vertex set of H. So it gives you an object that you've removed. If you find one of them, then you must find many. That's the point, right? So the point is that whatever H you have, suppose you find... So yeah, so this is not the right thing to do. We want to remove all of these things. But suppose after removing these edges, we find a single copy of H somewhere, right? I mean, on some number of vertices. So here's some edges. These are all edges of H. But then all of these edges of H must be edges of R. So this object is contained in R. But H is contained in this object that's in R. So by the embedding lemma, you have not just one copy, but many copies. Contradiction. Right? That's what regularity does for you. It takes, if you take and find one copy, it says, then you have a positive density of copies. Does that make sense? Well, one copy, that corresponds to something in R. Right? This is why R is a useful way of thinking about the graph. Questions? Does that make sense? Okay.
So you have to remove the KR and the graph itself.
Oh.
And generalize it here.
No, so yeah, so you tell me. What are you supposed to remove? What was the proof? The proof was, so there are various ways you could find h, right? You could find a C5, for example, in a C5 or in a triangle. With a more complicated h, you could find it in lots of different ways. So you have to remove any object in R that gives you a chance of finding h. So what does it correspond to? Suppose you find a copy of h somewhere. Let's do it for the cycle again. So you could either put them in 5 different classes, or you could put them in 3 different classes. What we're doing, right? Like that. Or I guess you could put them in 4 different classes. Can I do this? No, probably not, right? Because then I have to have. Yeah, I can put in 4 different classes. Right. So then you just go. Right. 8. So you can do 1, 2, 3, 4, whatever, 2. Right. So what am I doing? I'm just colouring the vertices without allowing 2 adjacent ones to have the same colour, and using at least 3 colours. I mean, okay, of course using these 3 colours. So for any colouring, you get a corresponding object. So here's the object here. It is a triangle with an edge coming off it. Okay, that's a bit stupid, right? Might as well be a triangle. Right? But for each of these, remove the corresponding object. Right. Sorry? Sorry, the number of them.
É o grafo completo com o número de vértices de H. Você promover todos os cassinos de G.
Sorry, so we have to get rid of C5. We also have to get rid of whatever graph comes out of any other colouring. Right, so we have to remove F such that, such that H is contained in a blow-up of F, sorry. Right, so this is a blow-up. This is where you blow up each vertex to size T and put complete bipartite graph between pairs corresponding to an edge. Right, and so it's just remove anything that the embedding lemma works for, and then you must remove all the copies by doing this, by definition, because that's what the embedding lemma does. Right? If in the embedding lemma you can find a copy, I mean, if in the complete thing, in the blow-up, you can find a copy, the embedding lemma says in the real world you find many copies. Right? But if in the blow-up you don't find a copy, then this destroys all of them. Yeah.
If I have a very large graph
Yeah.
with low chromatic number,
Yeah.
then I'll have lots of.
Absolutely. What's wrong with
you
that?
say it's bounded, but for me it's.
Oh, but it's just bounded, right? It's just a constant.
But it's going to be n squared.
No, I mean h is fixed size. This is all h. Everything depends on h. Right? Fix h and fix alpha. And then these guys depend on h and alpha. Right? So h is not allowed to have size root n or something.
No, sure, but I want to remove n squared edges, right?
Yeah.
We're going to.
Alpha n squared edges.
Yeah, alpha n squared.
So the only edges you remove are these. You only ever remove delta plus 2 epsilon times n squared edges. You never remove anything else. This is just saying these things, you're not removing these f, you're saying they don't exist. Because if they did exist, it would contradict the assumption. Right? Because you would have at least this many. Right? This bound does not depend on f. Right? This is just some constant depending on delta, function of alpha and h, and k1, function of epsilon, which is a function of delta, which is a function of alpha and h. Right? This is just beta of alpha and h. Right? It works for any f. So you can do it for all of the f's. None of them exist, because if any one of them existed, you'd have a contradiction. Yeah, exactly. Okay, cool. Yeah, we don't have to sum over these things.
Yeah, I was confused.
Right.
Sorry.
Right. Okay. More questions? Yep.
If you remove the dot edges,
Yeah.
then you need alpha less than 2 epsilon plus delta.
Yeah. Alpha is at least delta plus 2 epsilon.
But it was for all alpha, so you want delta and epsilon.
So yeah, so delta is a function of, yeah, so let me write it again here. Yes, maybe,
Embedding lemma.
yeah. So alpha is much smaller than 1, right? It's arbitrarily small. We pick delta much smaller than alpha. I mean, actually, alpha over 2. Right? And then we pick epsilon much smaller than delta. And this needs to be much smaller because we need to apply the embedding lemma. In the embedding lemma, epsilon needs to be small compared with delta and h. And then beta is this crazy function,
Because the embedding lemma says
but it's still positive.
an epsilon, right?
Yeah, for all delta, exactly. For all delta.
Take, an epsilon that is less than that epsilon, it still works, right?
Yeah, sorry. The statement is monotone in epsilon. Yeah, so you take epsilon as small as you like. Yeah. Yeah, it's not just there exists one floating around. It's, yeah, so it's all sufficiently, all smaller ones, yeah.
Smaller than
Exactly.
that epsilon.
Yeah, there exists an epsilon 0 such that for all smaller epsilon it works, yeah. Thank you. Yeah, so we can do this in particular.
Sorry,
Yeah.
just one more thing. Why for every type of f it will appear power of v of h? Because I want to get a contradiction to get bigger than.
Yeah, so perhaps let's just look at the C5 in the triangle. So what do you do? So you chop it up into pieces that are size sort of number of vertices of h. Yeah, and then you just look for, then you pick whatever 5 of them to be in, and then yeah, you find the thing.
It will be essentially the same thing, but
Yeah.
two vertices the same.
Yeah. Yeah, we just write out the proof or whatever, and you see that. Yeah, so maybe it should be 1 over k1 times v of h to the power of v of h. More questions? Okay. Question about a different topic? Did you manage to do the counting problems on the example sheet with regularity? Did anyone manage to do the counting problems on the... So, maybe I should do those. So the theorem, this is a theorem of Erdös, Kleitman, and Rothschild. From the 70s. They did not use regularity. This was, 70s, so regularity existed, but only just existed, and I think people didn't really know how to use it yet. Anyway, so they proved something much stronger than this, but let me say what this result. So how many triangle-free graphs are there with n vertices? What's funny? Yeah, that. So give me a lower bound. Go to the proof of the lower bound. Yeah, exactly. Take any bipartite graph. Just take a bipartition. Here you've got n squared over 4 edges. Any subgraph works. Okay. So what about the upper bound? Sorry? You do this, right, exactly. Right, so how do you count? So apply regularity. So take any G that's triangle free, apply regularity, and observe that there's no triangle in reduced graph.
Are we assuming a lower bound on the edges of G?
No. So it might be the reduced graph is empty. Right, so if G is sparse, then the reduced graph will just be empty, but okay, this is still true. Right?
So what's the strategy for proving the equality?
Okay, so let's see. So what we're going to do is we're going to count by according to Szemeredi partition. So you should think of you're taking all of your triangle-free graphs and you're going to partition them, or not really partition them, you're going to cover them with a fairly small class of containers, you could say. Okay, so you're going to take each Szemeredi partition is going to define a container which contains lots of triangle-free graphs. You're going to be able to count each one of those individually and then sum over the containers, of which there are a few. Okay, so what are we going to do? So first, the question is, how many Szemeredi partitions are there? The number of Szemeredi partitions is at most what? I mean, I'm going to say so many partitions. Yeah.
You've got a graph with 3 of K3 and you're bounding.
Yeah. So
Oh, sorry, I didn't get what you were doing.
sorry. So I was going to do the proof in a different direction, but then I was asked to do it this way, so I changed suddenly direction. So this doesn't really lead naturally here, but we change course. So we're going to count triangle-free graphs in 2 steps. First, we're going to count the Szemeredi partitions, like how many choices you are for a Szemeredi partition. Then we're going to fix a Szemeredi partition and a reduced graph and say, all right, given this partition and this reduced graph, how many choices are there for G? I'm going to multiply these 2 numbers together. And that's going to give us a bound for the number of triangle-free graphs. Okay? So first, how many containers do we have? How many different Szemeredi partitions are there and reduced graphs?
Wait, but the theorem guarantees only one partition.
Yes.
The theorem. So
Right. So, but we want to sum over all partitions that we might have. But we're counting. We're not counting one graph. We're counting all graphs. So different graphs might give different partitions. Right? So we want to know, if we want to count the graphs, first we have to count the partitions, and then for each partition, let's count the graphs with that partition. Right? Each graph has a partition. Let's count the graphs with that partition. Yeah, so the theorem says that you have counted all graphs, because every graph has a partition. Right? Every graph may have many partitions, but okay, fine. So, once again, how many partitions are there? Well, notice that we have some stupidly big error bound here. Like, we're allowed to throw away factors of 2 to the little o n squared. And how many partitions are there of the numbers 1 to n into whatever number of pieces? Not that many, right? Like n to the n. Let's just bound this in a totally stupid way by n to the n. Okay, without even thinking about it. Right? And it's still n to the n is still way smaller than 2 to the little n squared, so I don't care. Right? Okay, so now let's fix an r and count the number of okay, so fixing the partition and fixing R, how many ways are there to choose a graph that's triangle-free? So first observation is, if R has a triangle, then 0. Right? You're dead. So we can assume that R does not have a triangle. So that tells us that R has at most how many edges? K squared over 4, right? Where k is the number of parts in the partition. Okay, so now how many choices do we have for the edges in G? Well, for each edge of R, how many choices do we have? At most. So suppose this is an edge of R, Vi, Vj. How many choices do we have for the edges here? Yeah, exactly. We have basically no information. So it's 2 to the n over k squared times the number of edges of R. Right? That's for just the ones that correspond to edges of R. And what about the rest? Well, what are the other edges? There, here, here, and here. How many are there? The most, like, delta n squared. So how many ways can there possibly be to put in delta n squared edges? At most, n squared, choose delta n squared. You just throw them in anywhere.
Can you repeat that, the choose part?
So this part? Yeah, so by this argument, there's at most delta n squared, 2 delta n squared or delta n squared, whatever. I mean, let's not worry. There are very few edges left over. So how many ways are there to choose them? At most this. Right, there's at most this many ways of choosing them. This is just putting them in any way you like. So you just now throw in delta n squared extra edges and don't even think about where they go. Just wherever they go. I mean, either they work or they don't work, just count them anyway.
So you are using the information that K3 is not on G, only on the first bound, right? Between
Yeah, so I'm not using it here at all. I'm using it here. Yeah, only here. But now we're going to plug this in and get that this thing is at most, with apologies to the camera, okay, maybe I'm going to stay in, n squared over 4 plus, what's this thing? This is like 1 over delta to the delta n squared, which is like, I mean, it's at most root delta n squared. Really, it's like delta times log 1 over delta. Yeah, but the point is it goes to 0. Well, we'll just write delta prime. Whatever. Delta prime tends to 0 as delta tends to 0. So if we want to get a little o n squared, we need to take delta going to 0, which is fine. We can do that. Right? We just take epsilon tend to 0 faster.
Sorry,
Yeah.
there you mean choose delta n square or delta plus 2 epsilon square?
Delta plus 2 epsilon, but just by shorthand. Yeah. Right. Well, now we're done. That's the proof. So the number of graphs is at most this times this. Right. This thing is 2 to the little o n squared. This is 2 to the n squared over 4. And this delta is going to 0 if delta goes to 0. So whatever bound you want to prove, we just choose delta small enough, and then epsilon small enough as a function of delta, and then n large enough as a function of epsilon. Right? So if we want this thing to go to 0, we can make it go to 0 by sending n to infinity. Right?
I'm sorry.
Yeah.
What is k again? The number of
Parts in the partition.
parts? Okay.
Yeah.
The k.
Yeah. Yeah, so k is a constant. Exactly. Yeah. I mean, a very large constant. And how about the next problem on the example sheet?
I could just suppose that the number of edges in G was bigger than the Turan. K squared over 4. No,
N squared over 4?
n squared over 4 plus little n squared.
So then it would have triangles.
Yeah, so we suppose that we don't have
Uh-huh.
triangles, and we have terms, so we would have a upper bound.
Yeah, so you know that your graph has at most n squared over 4 edges, but that's still too many to deduce this.
But it would be 2 to the n squared over 4 plus a little n squared.
So no, just the fact that you know, so the fact that E of G is at most n squared over 4 tells you that the number of these things is at most n choose 2 choose n squared over 4, which is actually roughly 2 to the n squared over 2. Right? It's actually much bigger. Even so, a typical graph, a random graph with density a half, has about this many edges. Right?
I'm saying that we suppose that E of G has more than
Uh-huh.
square over 4 plus a little n squared.
Uh-huh.
We would conclude that we have a triangle.
I mean, even if it's just strictly greater than this, then you have a triangle. Right? No need for little o n squared. Just strictly bigger. So we know that it's smaller. But it's not enough to prove a good bound on the count, because actually half of all graphs satisfy that property. Yeah?
I tried to use that if the number of edges in G is n squared over 4 minus t
Mm-hmm.
and doesn't have a triangle, then
Mm-hmm.
the longitude is
Yeah.
longitude.
Yeah, close to bipartite, yeah.
And then try to
For this one.
didn't work.
Yeah, so
I don't understand really why, because I thought that being close to bipartite was like something.
right, so yeah, if you're close to bipartite, then it's a lot of information. But the trouble is, it's a very strong assumption. So actually, how many edges do most triangle-free graphs have? What does this imply that most triangle-free graphs have? I mean, perhaps imply is a strong word, but you can read out of this proof more or less, I mean, how many edges a random triangle-free graph has, as in a uniformly chosen triangle-free graph. Can you see what it is? Where are most of the edges in this counting? Yeah, right? I mean, or let's say in this construction, right? We took a random subgraph of this thing, an arbitrary subgraph, so typically a random one. So you keep about half of these edges, so you have about n squared over 8 edges. So most of the ones you want to count don't have n squared over 4, or n squared over 4 minus t, unless t is huge. They have n squared over 8 edges. So they're way, way sparser. So yeah, so you can't just apply these extremal things. you have to do something like this. However, the stability is useful for the next problem, which said what? So I'm not sure who proved this actually, but anyway. Is that right? Was that the next question? Yeah. So how do you prove that? So you're all looking down, but you should be looking up, because it's basically you do this, but slightly different. Right? What do we change about this proof?
The number of the that don't have H, 3, and
Right. So yeah. Okay. What we're trying to count. So we want to count the ones. So should be a little o. So how are we going to prove this? What we want to say is that there are many triangle-free graphs and many fewer that are far from bipartite. So how many are there? We know how many there are. There are at least 2 to the n squared over 4. So we'd like to show there are many fewer that are far from bipartite. Okay, so let's just count the ones which are far from bipartite. So I guess there are 2 cases. You're all looking very confused. You should be all jumping on top of this. Come on, it's like there. It's right there. It's ready to bash it over the head. You even know the tool you're going to use. Sorry, go on.
Can you repeat that bound?
N sort of 4, it's just bipartite. Subgraphs of that guy. Right? And they're all close to bipartite because they're bipartite. Right? Yeah. Right, so what do we do? So there's 2 cases. Either R is close to bipartite or it's far from bipartite. So suppose first that R is far from bipartite. How can you improve this argument? Yeah. Yeah. Use stability on R, not on G, on R. Right? By stability, if R is far from bipartite, then you gain an extra whatever here. I don't know, let's write delta K squared. Okay, so either R has fewer edges or you're close to bipartite. R has fewer edges. What do we get here? Maybe I don't want delta. I want alpha, sorry. New alpha. Because I want alpha to be bigger than delta. So what do we gain? We just plug it straight in here. Right? And we get a minus alpha n squared. So if alpha is bigger than delta prime, then this is tiny. Right? So the ones where R satisfies this are way smaller than this bound. So very, very few, super exponentially few, have a reduced graph with fewer than that many edges. So we only need to count the ones where R is close to bipartite. But if R is close to bipartite, then what? If R is close to bipartite, then G is close to bipartite, right? Because right, here's R. There's some bipartition such that there are very few edges of R inside. Most of them are across. So which edges of G are there? There's like a few of correspond to R plus these guys, but it's still few. Right? So in that case, they're close to bipartite, so they don't count here at all. So in fact, what we proved is not only almost all, but the number that are far, the number that are alpha epsilon far is at most 2 to the n squared over 4 minus basically alpha n squared. I mean, I'll put 2 here to be safe. Right, so really, really, really few of them are far from being bipartite. And in fact, Erdős, Kleinman, and Rothschild prove more. Yeah, sorry, it's also their theorem. They proved not only are almost all triangle-free graphs close to bipartite, they show that actually almost all are bipartite. Right, something much, much stronger is true. So I removed this part of the statement, and this is actually what these guys proved. They proved almost all triangle-free graphs are not only close to bipartite, they are bipartite.
I'm sorry, Ron.
Yeah.
It's not only little O of n squared, right? It's little O of 2
It's
power of minus.
yeah.
Yeah, it's much smaller. It's little
Sorry.
o n squared.
Sorry. Little o n squared is how close to bipartite they are. Yeah. But the proportion is not, so the almost all is in a very strong sense. It's really very few of them are not very close to bipartite. And actually, almost all are actually bipartite. But then it's really just almost all. Like the cost of not being bipartite is roughly, maybe it's still exponential. It's still exponential. Sorry.
Just to clarify, when you
Yeah.
say almost all, you say that the ratio goes to 0.
Yeah, exactly. So if I put all of the triangle-free graphs and vertices in a bag, and I pick one out randomly with high probability, it's bipartite. Yeah. Yeah. More questions? Did anyone manage to do the extremal number of C5? So I've forgotten to do this, but maybe we can try. It's also related. Right. So this is a nice example of an exact result you can prove with the help of regularity. So first I want to show that, so what I'm trying to prove, the extremal number of C5 equals n squared over 4. Let's assume n is even. For simplicity. Right. So as a first step, I would like to show that if, so let's take a graph that's C5 free. So what do we know about this graph? We know that the number of edges, let's assume the number of edges is bigger than n squared over G. We assume it's at most n squared over 4 plus epsilon n squared by Erdös-Stone. Right. Or by applying regularity or something. What I want to show is that first this graph must be close to being a complete bipartite graph. I guess that follows already from Erdös-Simonovitz, right? What am I doing? Yeah, so by Erdös-Simonovitz, implies that G is epsilon n squared close to being bipartite. Is that right? Or, right, otherwise we'd have to have fewer than n squared over 4 minus epsilon squared edges. Right. So we're already close, so how do we finish off? So we have something that's sort of close to being bipartite, and then there's some edges inside. So where do we expect to find, how do we expect to find a C5? We think basically if there's an edge here, then you can go done, 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 and get a C5, right? That's what we think. And the great strength of this thing is that is this vertex. We have a large number of choices for this vertex. Right. So what should the idea be? Well, okay, so let's draw this picture again. Maybe I'll draw a bigger version. Let me do a bigger version here. So we have two vertices, we find an edge between them, and now we want to find a C5. What do we know? Well, these guys should have very large degree, right? Typically, vertices have, in this graph, have, degree half of the whole thing. And then all you need is to have one other vertex somewhere that intersects both this part and this part. Right. This doesn't seem very difficult to find. So how are you going to find it? Well, I guess a good first step would be to make sure that every vertex on this side has many neighbors on this side. How are we going to do that? Let's do like a first step to make sure we can do that. First, why does every vertex have large degree? Sorry? No, so even before, so no regularity, just. Yeah, perhaps we didn't need any of this. I'm not quite sure anyway. So just from the beginning, I would like to claim that in our graph, every vertex has large degree. You tell me, well, how are you going to do that? There might be a vertex of small degree. What should I do with this particular small degree? Throw it away and apply induction. Right, let's do an induction on n. This is a statement for every n. If we have a vertex of low degree, throw it out, apply induction. Okay, so what's our minimum degree condition that we can assume? So if there exists V with degree at most, let's call it k for now, number of edges of G minus V is number of edges of G minus k, which is at least, if the previous one was at least n over 4, so n squared over 4 minus k, which should be at least n minus 1 squared over 4. And this is true if k is at most, basically n over 2, right? N over 2 minus a bit. So if there's a vertex of degree smaller than n over 2, which is the average degree, you can remove it and apply induction. Okay, so every vertex has degree at least n over 2. That's pretty good. So this guy should have neighbours everybody here. Except what if it has lots of edges inside? There aren't many edges inside, but there's like epsilon n squared. So it's not so great.
Why are you worried about the edges inside?
So I want to say that if there's an edge here, then we can find a C5. So I'd like to say this pair have many neighbours over here, so many that we can pick another vertex and find a C5. But we can't do that if most of their edges are inside. And there might be some vertices inside with high degree inside. Right? So let's deal with them first. So case 1, what if there's a vertex with very high degree inside? Let's say this is epsilon times n. At least epsilon times n. Maybe we want to call it, I don't want to call it epsilon, we want to call it alpha times n or something. So I think what I want to do is pull this guy out. So one possibility is he has almost all edges here and not many over here. But then he should be on the other side, right? So we can assume he has at least alpha n to both sides. We can choose alpha later. Sorry. So we're going to take a bipartition. We're going to take a maximal bipartition. So a maximal bipartition, every vertex has at least as many edges across as they do inside, otherwise you'd swap sides. And then we're going to suppose there's a vertex in one of the classes with degree at least alpha n inside his own class, and therefore the other class as well. So suppose there's this vertex with at least alpha n neighbours on both sides. Now I want to find a...
Then we use this vertex to create our C5.
Yeah, exactly. So what we want to find is something that looks like this. Right? How do we find that? So, we haven't used this property yet. Let's try and use it now. Let's actually take out all vertices that have very high degree to both sides. So everyone else inside here has very high degree across. And observe that how large is this set? It's very small, right? Because G is close to being bipartite. Right? But it's little o n squared close to being bipartite. There's a little o n squared, little o n vertices here with these high degrees. And so they still have high degree in what's left. Alpha n over 2, say. And now everyone left here has high degree across. And so what should we do? I guess we take any vertex here and any vertex here and look at the neighborhood. It's huge. Look at this neighborhood, and it's huge. It's almost everybody. And so if we don't have an edge across here, we have basically no edges. So we're done. Right? OK. So that doesn't happen. So there's no vertex of high degree inside. So everyone has very high degree across. So everybody has degree little o n inside and a half minus little o one times n edges across. How do we find a C5 now? Well, take any edge here. This has a neighborhood almost everybody. This one has neighborhood almost everybody. So the common neighborhood is almost everybody. And now any vertex here also has huge neighborhood. So there's a huge neighborhood here. And now I claim we have a C5. 1, 2, 3, 4, 5. Any pair of vertices in here. So we didn't just find one. Actually, we found many. Right? Yeah, you can basically choose these, you put n cubed of them or something. Yep.
Where did we use that number of edges is greater than n squared over 4?
Just to show this edge exists. The only time, only once, exactly then.
So it could be exactly n squared over 4 plus 1.
It could be, right, so even if it's n squared over 4 plus 1, yeah, so the only, right, so you're close to bipartite. If there's any edge inside, you already have a C5. So you really must be a subgraph of a bipartite graph. And this is true, right, just using this. So it's using bistability.
Wait, but
Yeah.
if I have n squared over 4 plus 1,
Yeah.
can I apply the Erdös?
Right, so the Erdös stability, you need to know that the number of edges is at least n squared over 4 minus epsilon n squared. Yeah, so this says something stronger. It says that, unless I'm cheating, that if you're... no, yeah, so it doesn't say something stronger. I am cheating because of this argument. So what I wanted to say was, it says that if your number of edges is bigger than n squared over 4 minus epsilon n squared, then you must be contained in, and your C5 free, you must be contained in a bipartite graph. But it's false, of course, because you're allowed to have things like low degree vertices, right? Then the induction doesn't work. So the induction was really just for showing we were proving only this. But once you've removed all the vertices of low degree, so once your minimum degree is large, you really get this structural result. I think this was maybe first observed by, or proved by András Fáy, Erdős, and Sós. This is their theorem.
What's the construction for the polygon?
Oh, complete bipartite. Because its chromatic number is 3. Yeah.
I'm not completely convinced that
Yeah.
if I get n squared over 4 plus 1,
Ah.
I will have a C5.
Aha, OK. So that's this argument here.
Yeah, but so why did you do that? So I'm slightly confused.
So suppose you...
I will have to show that if I have n squared over 4 plus 1, I will have a C5.
Exactly. It's exactly what you have to prove.
Yeah.
So first step, if there's a vertex of degree smaller than n over 2 minus a bit, remove it and apply induction. OK. So now I have a minimum degree condition. OK. Next step is apply stability to show that we're close to being bipartite. Third step is to do this argument to show that actually we're not only close to bipartite, but every vertex inside the parts has low degree inside. And the fourth step is to say, right now, either we're bipartite, in case we're done, or there exists an edge in one of these parts. If there exists an edge, it's in roughly n cubed C5s. Right. Does that make sense? Yeah. So I think this proof is so it's difficult to find if you're not used to doing these things. But this actually is by now a fairly standard. So I was able to sort of rediscover this just now because this is by now a fairly standard thing to do, right? I mean, this is just what you do in this kind of situation, right? So yeah, so you should, if you want to prove a result like this, get it close to what you want, then deal with kind of local impurities, like high-degree vertices, and then once you've got rid of all of the local obstructions, then just try and argue by some kind of brute force. Right? This is now a fairly standard thing. So you shouldn't, this may look like a totally ad hoc thing to do. It's not. This is really a general method for attacking this kind of thing. And I think Szymonowic, maybe this is his proof, he proved that for any edge-critical H, something so much more general is true in like the 70s or something. I mean, it's an old argument. OK, so we should stop. Monday. Well, so on Monday, if you have more questions, we can do more questions. Otherwise, I'll do something different. Okay. Any more questions? OK. Maybe I'll send you a third list, or maybe I won't. Anyway, if I do, I mean, you shouldn't feel obliged to do it. It's just, for fun.